Hey guys, welcome back to chapter 6. So we're going to talk about in this second and final video from chapter 6 is something called sigma and pi bonds. We're going to start to look at more complex molecules and talking about the different types of bonds. And then the last thing I'm going to leave you with is expanded octets and what the hybridization looks like for those guys. So first things first, there's going to be two types of bonds that we talk about with the valence bond theory. The first type of bond that we talk about is something called a sigma bond. So a sigma bond is just going to be your standard single bond. So sigma single, sigma single. There is a plethora of ways that you can make a sigma or standard bond. It can be just the standard S to S overlap. It can be a standard P to P overlap. It could be a hybrid to hybrid, or an S to hybrid, or a P to hybrid, or a D to hybrid, or a D to D. There's just any combination of ways that you can do sigma bonds. So sigma bonds are your single bonds, and there's a plethora of ways to make them. Okay. So here's an example of sigma bonds. So here's an S overlapping with a hybrid. So this would be an example of a sigma bond. And again, if I were to draw that bond from the Lewis theory, it's just a single regular old bond that looks like that, right? So here's our sigma bond. Okay. A pi bond is going to be our double bond. So our pi bond is our double or our triple bond. And while there is a plethora of ways to make a pi bond, while there's a plethora of ways to make a sigma bond, there's only one way to make a pi bond. The only way to make a pi bond is overlap between unhybridized parallel p orbitals. That is the only way to make a pi bond. So pi bonds look kind of funny right here. They look like balloon animals, honestly, to be honest with you. But pi bonds are these big overlapping bonds here, okay? So unhybridized p orbitals tell me that they're just going to be those double-lobed, red going up, red going down. And then parallel means that they're going to be parallel to one another. So if I have one p orbital here, another p orbital here, those are running parallel to one another. And again, I'm without my pen right now, so please forgive me for the mess. Good enough. All right. So see how these are parallel to one another? A pi bond would be this guy reaching over to this guy, and that would be a pi bond right there. Okay. The interaction between parallel orbitals is not as strong as between these head-on hybrid orbitals or hybrid s orbitals. So sigma bonds or single bonds are stronger than pi bonds. So here's just another look at what a pi bond, a much prettier look at what a pi bond looks like versus a sigma bond. So this top bond here is a pi bond. So right here we've got side-by-side overlap. Parallel unhybridized p's, they reach over, they make a pi bond here. This right here is actually an example of a sigma bond. So here we've got head-to-head overlaps. These guys are coming head-on and crashing together. So that head-to-head overlap is a pi bond, a sigma bond. Gracious. So down here is sigma, up here is pi. Okay. So only one way to make a pi, and that's parallel unhybridized. Okay. So looking at an example. So here we've got formaldehyde, right? And in formaldehyde, let's talk about what we see. So carbon is our central atom. We've got a single bond to hydrogen here. We've got a single bond to hydrogen here. When we talk about multiple bonds, so double and triple bonds, the first one will always be a sigma bond or a single bond. So here's a sigma bond with oxygen. And the second bond, or third if it's a triple, will be our pi bonds. So we've got sigma, 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 and then this guy up here would be pi. So let's see what that looks like in 3 dimensions. So again, the first time you see this, it should look like a hot mess, but let me talk you through it and start to train your eye to see things. All right, so here's our carbon atom. Here's our central atom, okay? So we've got a sigma bond to hydrogen. So this bond right here and this bond right here are the same thing, okay? Sigma bond to hydrogen. Another sigma bond to hydrogen. So carbon, hydrogen, single bond, sigma bond. The first bond with oxygen is a sigma bond. So carbon, oxygen, the first bond here is a sigma bond. So we've got a hybrid orbital overlapping with a p orbital. That's a head-to-head overlap. So that's going to be our sigma bond here. The second bond between carbon and oxygen is our pi bond. So we see this p orbital that's going up from carbon. I see this p orbital that's going up from oxygen, and they reach over and touch each other, and that's our pi bond, okay? So sigma, single, pi, double, okay? Remember when I told you guys sp2 hybridization? Remember sp2 hybridization is trigonal planar. And then I said the p unhybridized p orbital is perpendicular to that. Well, here's where that comes back and becomes important. So here we see that carbon did sp2 hybridization. So it's got 1, 2, 3 hybrid orbitals. So I know that it must have put 1, 2, 3 standard orbitals into the mix. And where did that last p orbital go that was not hybridized? Well, it went perpendicular. It stuck up and stuck down. And that perpendicular p orbital, unhybridized p orbital, became very, very important when this carbon decided it wanted to make a double bond. Okay. Here's another example of sigma and pi bonds. So here's our original molecule, and we see a triple bond. So I just want to take a look at what a triple bond looks like here. So again, carbon going left is going to be a single sigma bond with hydrogen. So carbon going left, single bond, sigma bond. The other carbon going right is going to be a sigma bond with hydrogen. So here's the other carbon going right, sigma bond with hydrogen. Now this triple bond. So the first bond between carbon and carbon is always going to be a single bond or a sigma bond. So let's just, for example's sake, say this middle one is the sigma bond. And this guy has 2 pi bonds. So this bond on the top would be pi. This bond on the bottom would be pi. So let's look at that in 3 dimensions. Carbon, carbon. The first bond in the middle is a sigma bond, so head-to-head overlap of hybrid orbitals. Then that top one is a pi bond, so 1 bond, 2 bonds, and then the third bond is also a pi bond. So 1 sigma and 2 pi inside of there. Okay. I am not going to ask you to draw this balloon animal, if you will. I'm not going to ask you guys to draw that on an exam, but there very well may be a picture on the exam, and I might point to an area and say, what kind of bond is this? So I may point right here and say, what type of bond is that? I may point to this and say, what type of bond is that? And so you'll need to be able to visually identify sigma and pi bonds. So the last thing that I want to talk about in this chapter are those expanded octets, okay? So the expanded octets, remember, can take on more than 8 electrons. So if we're taking on 10 and 12 electrons, I'm going to need more than just 4 hybrid orbitals coming out of our hybrid maker, right? So if I have 10 valence electrons that I want to share, 4 orbitals or 8 places to make a bond is just not going to work, okay? So for our expanded octets, that's when we reach into the D block and we make just a slightly bigger hybridization. So here we see sp3d hybridization. So I'm putting in the s orbital, I'm putting in 3 of the p orbitals, and I'm putting in 1 of the d orbitals. So I'm putting in 1, 2, 3, 4, 5 things. So I'm going to get 5 hybrid orbitals out. Put 5 in, get 5 out. That's going to give me the opportunity to make 5 bonds or have 5 unpaired electrons. So we see on this example where we've got 5 sigma bonds here, we see 5 sigma bonds in 3 dimensions. Okay. The last hybridization that we talk about is sp3d2. So with sp3d2 hybridization, it's exactly what it sounds like. I put in an s orbital, I put in 3 p orbitals, and I put in 2 d orbitals. So if I put 6 things in, I'm going to get 6 hybrid orbitals out. Now I have the opportunity to sigma bond with 6 other things. So here's our example. We see 6 sigma bonds and we see 6 sigma bonds. Just like the first 3, where we said that hybridization and electron geometry were related, same thing holds true for these other 2. So sp3d hybridization is always trigonal bipyramidal. sp3d2 hybridization is always octahedral, so that will always remain the same. Okay. So one of the things that you will see on your Chapter 6 lab is there will be a space to predict hybridization. So what I'm looking for the answer there is going to be something like SP or SP3 or SP3D2. So this is what your answer should look like in that column that says hybridization. That's the end of Chapter 6. I hope you guys found this helpful.